Last class we were discussing high Peclet number convection dominated transport as part of our course on fundamentals of transport processes. The convection diffusion equation that we had, within that if we scale all velocities by the flow velocity and all lengths by a characteristic length, the equation has the convective term on the left multiplied by the Peclet number and the diffusion term on the right. After solving diffusion dominated flows when the Peclet number is small, we had now come to considering convection dominated flows where the Peclet number is large. And at steady state, if you just make the simple approximation that the temperature field is no longer a function of time, the equation basically reduces to an equation of the form u dot grad T is equal to del star square T, okay, with the Peclet number in front of it. That is the form of the equation you get. If the Peclet number is large, you might expect that you can neglect this term altogether, and then you will get an equation which basically tells you that the gradient of the temperature dotted with the velocity is equal to 0, which means there is no variation in the temperature along the velocity vector or along the fluid streamlines. With that kind of an equation, you can no longer satisfy the boundary conditions at surfaces, because typically at surfaces you require that the temperature or the flux at that surface has to be equal to 0. And if you just assume the temperature is a constant along streamlines, you can no longer satisfy this condition. So, we had looked at how to resolve this issue. Okay. What we had done was to write down the temperature at any location x as a function of a similarity variable eta, which is y divided by delta of x, where delta of x is the boundary layer thickness, because we know that convection and diffusion have to be of equal magnitude within a thin boundary layer near the surface, even in the limit of large Peclet number. The thickness of this layer decreases as the Peclet number increases, but within this region both convection and diffusion are of equal magnitude. So, using the similarity form, we had derived an equation for the scale temperature field in terms of this similarity variable. And from the condition that a similarity equation can be solved only when this is a constant, that basically gave us an equation for the boundary layer thickness delta. Okay. In this particular case, the boundary layer thickness delta is obtained by solving this equation. It goes as x to the 1/3 power. Okay. So, one is the expression of the cross stream variable y in a similarity form. That transformation involves the boundary layer thickness. The next is the solution of the temperature field in terms of the similarity variable, and that temperature field in terms of the similarity variable is here. Okay. And that temperature field contains two constants. Those constants can be determined from the boundary conditions, that at y is equal to 0 or eta equals 0, the temperature is 1. Far away or at the start of the heated section, both of which correspond to eta going to infinity, the temperature has to decrease to 0. And we had obtained an expression for this. From that, we can calculate the heat flux, okay, Qy as minus k dt by dy. You get it in terms of the similarity variable. Since we have solved for that similarity variable, we can find out what is the heat flux as a function of the downstream distance. Note that the heat flux decreases as x to the minus 1/3, because the boundary layer thickness increases as x to the 1/3. So, it has a power law scaling with downstream distance. Okay. And from that we got the average heat flux, and from that the Nusselt number. The Nusselt number in this case goes as Peclet number to the 1/3 power. Okay. And that is because the convective term on the left side was proportional to the Peclet number times the boundary layer thickness, because the velocity was increasing linearly with distance from the base. So, within a thickness of order delta, the velocity is proportional to delta itself, because it is increasing from the wall. So, because of that, the left side is Peclet number times delta. The right side has two derivatives with respect to y. That means it goes as 1 over delta square. So, therefore, if Peclet number times delta is proportional to 1 by delta square, then the boundary layer thickness has to go as Peclet number to the minus 1/3 power. Okay. So, that is the basic reasoning. And we had got a correlation for the Nusselt number as a function of Peclet number. It goes as 1/3 power. Boundary layer thickness decreases as P power minus 1/3. The heat flux is proportional to the gradient, which is proportional to 1 over the boundary layer thickness. Therefore, that increases as Peclet number to the plus 1/3 power. And I had extended this to you for the flow in a tube. The heat transfer from the wall to the bulk of the fluid within the tube. Okay. The average flux is the same as what we had calculated earlier, except that in this case I have to choose the strain rate at the wall of the tube in terms of the fluid average velocity and the fluid diameter. This is the parabolic flow for the flow in a pipe, where u is the average velocity. We had calculated that earlier by momentum balance. From that you can get what is the strain rate at the wall. Gamma dot has to be positive in this case. Okay. In this particular case it is negative because I have assumed that d by dr is the radial direction is the opposite of the y direction from the wall. Okay. So, the strain rate with respect to distance from the wall will be a positive number. Okay. So, I will have ux by partial y, that will be a positive number. Okay. Okay. And that was equal to 8u by particle diameter, the pipe diameter, I am sorry, and I just substitute that into this equation. Okay. And I managed to get an equation for the Nusselt number. This was the correlation that we have for a laminar flow. It goes as Re power 1/3, Pr power 1/3 times d by L power 1/3. All of these are what you have studied in the correlation for the heat transfer in a shell and tube heat exchanger, except that this constant is slightly under predicted by our analysis. Apart from that, all the scalings are exactly the same. So, this simple boundary layer analysis is actually able to give you the heat transfer correlation for a pipe. Okay. Of course, this is valid only when for delta is much smaller than the pipe diameter, because once the boundary layer thickness becomes comparable to the pipe diameter, I can no longer assume that the boundary layer is confined to a thin layer near the wall. Okay. So, that restriction is there. The boundary layer thickness has to be much smaller than the pipe diameter. Okay. The boundary layer thickness is equal to the length times Peclet number to the minus 1/3. Okay. This is the Peclet number based upon length. Okay. Has to be much smaller than d. Okay. Which implies that length, okay, times alpha by ul power 1/3 much smaller than d. Okay. Or alpha by ul much smaller than d by L the whole cubed. Okay. And this would translate into, okay, okay, ul by alpha, okay, is much greater than L by d the whole cubed, or ud by alpha is much greater than L by d the whole square. Okay. I multiply both sides by d by L. Okay. Therefore, the requirement for this analysis to be true is that the Peclet number based upon the pipe diameter has to be much larger than L by d square. Okay. So, once the length becomes large enough that this condition is exceeded, the boundary layer analysis no longer applies, and therefore, the correlation is no longer correct. The correlation is valid only so long as the boundary layer thickness is much smaller than the pipe diameter. That is a limitation of the analysis. And that is the reason once the boundary layer goes in to occupy the entire tube, you do not gain much more by having additional length of the pipe. Okay. And that is the reason for this factor here, d by L to the 1/3. Okay. because as L becomes larger and larger, this factor becomes smaller and smaller. Nusselt number no longer increases if you go to very long pipes. Okay. So, this is for a flow in a pipe where we managed to get the correlation. Let me go on to a slightly more complicated problem, that is the mass transfer from a spherical particle. Okay. I have a spherical particle of radius r, and I have fluid that is convected past this particle, okay, in a laminar flow. Okay. It goes around and comes down on the downstream side. In a laminar flow, these streamlines are symmetric between the front and the rear. Okay, in a laminar flow, these streamlines are symmetric between the front and the rear. The concentration far away is C infinity, and the concentration at the surface of the particle is some concentration C naught. And we would like to know what is the Sherwood number correlation for this configuration. Okay. Of course, this is a forced convection problem, and it is necessary to specify the velocity field in a laminar flow in order to be able to solve this problem. Okay. So, for this, it is most convenient to choose a spherical coordinate system, okay, whose axis is along the axis of the flow past the particle. Okay, because when you go around this axis that I have drawn here, okay, around this axis that I have drawn here in red, the velocity field is independent of angle around that axis. So, it becomes an axisymmetric problem. Okay. So, therefore, it is convenient to use a spherical coordinate system with this azimuthal angle theta, okay, which is the angle from this axis. Okay. So, the conservation equation at steady state, okay, okay, that is the convective side, okay, u dot grad c, okay, is equal to d into the diffusive part, the Laplacian of the concentration field. In a spherical coordinate system, we had derived that for you, 1 by r square d by dr of r square partial c by partial r plus 1 by r square sine theta. Okay. With boundary conditions, c is equal to c 0 at r is equal to r, and c is equal to c infinity as r goes to infinity. Far from the surface, the velocity, the concentration is c infinity. At the surface of the sphere, the concentration is c 0. Okay. So, this is the convection diffusion equation, okay, d del square c, where I have assumed that there is no dependence upon the angle phi around this axis. Okay. In order to solve this problem, you need to know what is the velocities u r and u theta. Okay. These have to be specified for you as part of the problem, because you will not be able to solve the problem if you do not know what the velocities are. Okay. For a laminar flow, these solutions can be obtained, and I will just write down what the solution is for you. U r is equal to minus cos theta 1 minus 3 r by 2 r plus r cubed by 2 r cubed. Okay. And u theta is equal to, let me write this, u sin theta 1 minus 3 r by 4 r plus minus r cubed by 4 r cubed. Okay. That is assuming that u is the incident velocity on the particle far from its surface. Okay. U is the velocity on the particle far from the particle upstream. Okay. Of course, the velocity gets distorted as it goes around the particle, and that distorted velocity profile is what is shown over here. Okay. So, subject to these two velocities and this concentration equation, we have to find what is the concentration field, and therefore, what is the flux, the average flux, and the Sherwood number. Scaling, UR star is equal to UR by U, U theta star is equal to U theta by U. Okay. Those are the natural coordinates. Okay. For length, the natural coordinate is R star is equal to R by R. Okay. And that is it. The other is the angle. The angle is already dimensionless, and I can write down the concentration as C minus C infinity by C naught minus C infinity. Okay. So, at R is equal to 1, this implies that C star is equal to 1 at R star equals 1. Okay. At the surface of the particle, C star is 1, and far away C star is equal to 0 as R star goes to infinity. Those are the boundary conditions that we have to satisfy in this problem. Note that in this case, close to the surface of the particle, the streamwise direction is actually the theta direction, because the velocity field is in the theta direction as the fluid goes past this particle. Okay. The streamwise direction is the theta direction, and the cross stream direction is the r direction. So, once we scale it this way, it is quite easy to see what are the equations that you will get. Okay. U r by d, okay, into U r star partial C star by partial R star plus U theta by R partial C by partial theta is equal to that is the radial part of the diffusion plus the azimuthal part. And the scaled velocities are u r is equal to minus cos theta 1 minus 3 by 2 r star plus 1 by 2 r star cubed u theta is equal to okay, so those are the velocities. Okay, those are the two velocities. And of course, this is the Peclet number. Okay, u r by d is the Peclet number for mass transfer. This is the Peclet number for mass transfer. We are considering the situation where the Peclet number is large, that is, mass convection is much faster than mass diffusion. The opposite case, where diffusion was dominant, we had already considered. We had actually found out that the Nusselt number was equal to 2 in that limit, when the mass transfer or heat transfer was entirely due to diffusion. Here we are considering the opposite case, where the mass transfer is entirely due to convection. When the Peclet number is large, if you just neglect diffusion, equation just reduces to u dot grad T equals grad C equals 0. Okay. So, the Peclet number is large, equation just reduces to u dot grad C equals 0, which means that there is no variation in the temperature along the streamlines, and what that means is the temperature is a constant along each streamline. Okay. And therefore, you cannot satisfy the boundary condition. It presents a discontinuous change from C infinity to C0 at the surface. That is because we have neglected diffusion. So, how do we take into account the effect of diffusion at high Peclet number? We have to postulate the presence of a boundary layer, okay, close to the surface, okay, boundary layer close to the surface of thickness delta. This thickness delta will in general be a function of the streamwise direction. The thickness delta will in general be a function of the streamwise direction. Okay. Along the surface, theta is the streamwise direction. And once we express the equation in terms of similarity variable, okay, eta is equal to the distance from the surface divided by delta. Okay. I will come back a little bit and define for you what is the distance from the surface in this case. But if we define it in terms of the distance from the surface divided by delta and balance streamwise convection and cross stream diffusion, we will find out what is this boundary layer thickness, such that the equation remains independent of Peclet number even in the limit as Peclet number becomes large. As you can see, the expressions for the velocities are rather complicated. However, I do not really need the velocity at all locations in the flow. I need the velocity only very close to the surface. Okay. And since we need the velocity only very close to the surface, I can expand the velocities in as a function of the distance from the surface and only take the leading contributions in that case. Okay. So, let us see how to do that. U r star is equal to minus cos theta 1 minus 3 by 2 r star plus 1 by 2 r star cubed. Okay. This was for a flow in which this was the angle r, this was the angle theta. Okay. Rather than expressing the coordinate in terms of the angle r, in terms of the length r, since I am interested only in a very thin region close to the surface, okay, what I can do instead is to expand out this region, okay, and define my coordinate as the distance from the surface. Okay, define my coordinate as the distance from the surface. Okay. I will define this coordinate as r star. Okay. R star is equal to 1 is the surface, because r is equal to capital R. Okay. R star is equal to 1 is the surface. The distance from the surface, I will write it as r star is equal to 1 plus delta times y, where delta is the boundary layer thickness. Okay. Delta is the boundary layer thickness, which goes to 0 as Peclet number goes to infinity in the limit as the Peclet number goes to infinity in such a way that convection and diffusion are of equal magnitude. So, delta is the boundary layer thickness, y is the scaled distance from the surface, such that the equation when expressed in terms of y is independent of Peclet number as Peclet number goes to infinity, so that in that equation convection and diffusion continue to be of equal magnitude. Therefore, I define r star is equal to 1 plus delta y, and then I have to expand the velocity in terms of r star. Okay. And use a binomial expansion for each of these terms. The whole square. Okay, that is for 1 by 1 plus delta y plus 1 by 2 into 1 minus 3 delta y plus 6 delta y the whole square. Okay. So, that is the binomial expansion for 1 by 1 plus delta y the whole cubed. Okay. And now you can see all terms of order 1. I have 1 here, 3 by 2 and 1 by 2, minus 3 by 2 and 1 by 2, and these will cancel out. Okay. If you consider terms of order delta y, I have plus 3 by 2 delta y and minus 3 by 2 delta y. Okay. Therefore, these terms will cancel out. Okay. If I consider terms of order delta y whole square, I have minus 3 by 2, okay, plus 3. Okay. Therefore, I have plus 3 by 2 delta y the whole square. Okay. That is the largest non-zero term in the velocity, okay, close to the surface, in the radial velocity close to the surface. Okay. So, this is going to be my expansion for UR, okay, in terms of y, minus 3 by 2 cos theta into delta y the whole square. Okay. Using a Taylor series expansion, in this case I had to go to second order in the expansion. You do not always have to go to second order, but if you go to first order and find out the coefficient is 0, then you have to go to the next order and find out what is the largest non-zero coefficient. Okay. You can do a similar thing for u theta. Okay. U theta is equal to minus plus sine theta 1 minus 3 by 4 r minus 1 by 4 r cubed. Okay, so that was the expression that I had for u theta. Okay, and I can expand this once again. Sine theta into 1 minus 3 by 4 into 1 plus delta y minus 1 by 4 1 plus delta y the whole cubed. Okay. Once again use a binomial expansion for this case as well. Okay. Okay. And once again these factors will cancel out, 1 3 by 4 and 1 by 4. Those will add to 0. However, I do have non-trivial terms at order delta y. Okay. Okay, so, the first term will be equal to plus 3 by 4 delta y plus 3 by 4 delta y, which is effectively equal to 3 by 2 times delta y. Okay. This is u theta star, I am sorry. You can see that this is equal to sine theta into 3 by 2 delta y. So, that is what I get by the binomial expansion. U theta has to be equal to 0 at the surface of the particle. The tangential velocity has to be 0, okay, because you have a no slip condition at a solid surface. For that reason, u theta is equal to 0. U r has to go as delta y the whole square, and the reason for that I will come to a little later. Okay. So, these are the expressions for u r and u theta. And now what I need to do is to put these back into the differential equation. I have got a greatly simplified form for the velocities, okay, which are valid only close to the surface. In the limit of high Peclet number, I am interested only in the velocities very close to the surface. So, I can use these velocities in order to find out what is the diffusion equation. Okay. So, for that I need to rewrite the diffusion equation u r star partial c star by partial r star plus u theta by r partial c by partial theta is equal to the whole thing multiplied by the Peclet number, okay, is equal to 1 by r square d by dr substitute in terms of the velocities, in terms of the variable, okay, r star is equal to 1 plus delta y, okay, and substitute for the velocities. Okay. So, I will get Peclet number into u r is minus 3 by 2 cos theta delta y the whole square. Okay. Partial c by partial r is 1 by delta partial c by partial y, okay, plus u theta was equal to 3 by 2 sin theta delta y, okay, divided by r, which is 1 plus delta y partial c by partial theta. Okay. On the right hand side, I have 1 by 1 plus delta y the whole square, 1 by delta d by dy of plus the second term, which is 1 by 1 plus delta y the whole square sin theta and since delta is small compared to 1, wherever I have 1 plus delta y, you can neglect it. Okay. And the final equation that you will get is minus is 3 by 2 Peclet number into cos theta delta y square partial c star by partial y plus this cos theta should have a minus sign there, plus sin theta delta y partial c by partial theta is equal to 1 by delta square partial square c by partial y square plus 1 by sin theta and within the boundary layer, as you know, this represents cross stream diffusion, because the y direction is across the velocity streamlines. It is the radial direction which is across the velocity streamlines. The theta direction is the streamwise direction, is the direction of the velocity. And since delta is small, you can see that the cross stream diffusion is much larger than the streamwise diffusion, because delta is small compared to 1, as it should be in boundary layer flows. The cross stream diffusion and the streamwise convection should be what are balancing, and in that case you can neglect the second term in the equation, simplify and solve using similarity solutions. We will continue that in the next lecture. I will see you then.